Good morning, everybody. Welcome to our machine learning seminar. Today, we'll have a pleasure to have a talk from Saurabh Deshpande from the University of Luxembourg, who will show the results and some insights of the recent work that has been done also in collaboration with me. So I'm the more happy to have this presentation today. Saurabh, please go ahead. Virtual floor is yours.
Just a second. So yeah, thanks Jakub for the introduction, and also it's a nice opportunity to say also thanks that everyone here must know that Jakub has huge contribution in all the work that I will be presenting today. So I will be talking about my recently published and one of the under review works on a new geometric deep learning framework called Magnet, as well as we talk about the state-of-the-art transformer based model for its uses in mechanics. A bit about myself. I am a final year PhD student at the University of Luxembourg. I work with Stefan and Jakub. My project is a part of Marie Curie ITN network, where I got opportunity also to spend some time at Professor Kotan's lab in India, Strasbourg. And prior to this, I worked for 2 years in the electromechanical design division at the Indian Space Research Organization, and I did my undergraduation and master's, integrated bachelor's and master's from IIT Madras, where I worked with Sundar, who is a close collaborator of Stefan. So the title of presentation says that learning scientific simulations, which is a broad word, and in the scope of this work, we'll be particularly focusing on applications to the mechanics of solids. So keeping the interest of general audience, I just give a brief introduction to problem statement. So you have a solid body, imagine this elephant, and you're applying the forces on it, and you're interested in predicting the deformed positions. So it's a static problem. And you do this by representing the continuous body in terms of number of discrete points. And these points are connected to each other and they constitute these small elements. And the method that we use to solve this particular problem is called finite elements. That's the preferred way to solve this problem using the conventional method. So if you go to your high school physics classes, everybody tries to attain a state of minimum energy, and that's what exactly we are trying to do here. We minimize the energy which we express in terms of some assumed constitutive laws, and we optimize it with respect to the positions to get the final optimal deformed position. But as you can already guess, it can be a nonlinear problem depending on the high value of forces, and it needs to be solved iteratively. And if you have more input force, you need more time to reach to the convergence. And therefore, it's not necessarily ideal for some of the application which demand real-time feedback. This can be the case in case of robotics or surgical simulations. So conventional solver are computationally expensive for these particular tasks. So there are some ways to increase the speed of computations of these conventional solvers using divide and conquer algorithm like domain decomposition method, or projecting this full field information to some reduced space, which is very similar to, if people are not from mechanics background, similar to, let's say, principal component analysis. So there are methods like proper orthogonal decomposition or proper generalized decomposition, which can increase the efficiency of your solution time, but still they fail to give accurate real-time simulation. There is a trade-off between the accuracy and the time of solution. And therefore, we would like to use machine learning models as surrogate models for this particular task. Just to be clear, what surrogate model means is just an alternate model which works really well for a particular defined task. So it might not generalize well in all the cases, but it works well for the particular task. So the general framework of these presentation, or the problems implemented in this presentation uh, can be summarized in this slide. So we have a continuous body which we will discretize in terms of finite elements that I just described above. and we pre-compute multiple solutions. So we apply forces in the prescribed range and we generate the displacement solution. And these pre-computed solutions are then given as an input to train the different type of neural networks. We'll see what type of networks we use later. And now this pre-trained network is then used to make a prediction on an unseen case, which was not the part of this training region. So that is more or less the idea behind the framework. So what type of neural network should I use for these applications? So again, to remind you, we are working on a full field prediction problem. We have a full mesh given and we want to predict some quantity of interest of that full mesh. So the dimensionality of input and output is same for our problems, which is equal to degrees of freedoms of the mesh. So degrees of freedom basically stands for the number of discrete points you have into the dimensionality of the problem, which is 2 or 3 depending on 2D or 3D problem. So fully connected networks do not really scale well for this kind of application. Imagine a simple network here on the left. You have n inputs and n outputs, and the number of parameters you have will be n square for this very naive network. And if you have, let's say, problem with 10,000 degrees of freedom, it already, the parameters goes to 100 million, which is huge. So it's not really ideal. And in such cases, the choice of convolutional networks works much better because we are sharing some parameters and we are performing basically some localized operation using some set of learnable parameters to get the output. So in the right figure, the bottom one is the input. We are applying the filter. This dotted region is called padded region. It's just adding zero values just to make sure that the output and the input will have the same size. So that's what we did in our first work, that we used a popular CNN unit architecture to train some of the force displacement pairs. So what we do is we have an input force mesh on which we apply multiple transformations like a convolution layer, the pooling layer, and at the end we get the deform mesh as an output. But it works really well for structured meshes, but it is only limited for structured meshes. There are some ways with which you can accommodate unstructured meshes with these kind of approaches. For example, one way to do so would be to find a parametric transformation between the unstructured meshes to the structured inputs, or embedding a grid and then just interpolating in the values of unstructured nodes to these grid nodes and then using it to CNN architectures. But these methods have their pre-processing cost, as well as you are expected to lose accuracy based on the complexity of the mesh, which is what motivated us to extend the concept of convolutional network to arbitrary graph structured inputs. So we call this network as magnet. It's a multi-channel aggregation network. The novelty comes from the fact that we have this notion of channels as you have in case of the CNN layers. And then the second type of layers are the pooling layers. Like if you have worked on CNN, you must be familiar with the max pooling or upsampling operations. And exactly, we propose similar type of operation for arbitrary inputs. And you have these concatenation links in between. They are used to first to avoid the problems of vanishing gradient, and also you pass on the information from earlier layers directly to final layers, and in a way it helps you to make the learning procedure easier. So they are I found quite important, particularly for mag layer. So magnet is a type of graph unit architecture. It is exactly like unit. Basically the unit name comes from this U shape that the architecture has. And it is composed of the two layers. First one is the multi-channel aggregation layer, as I described, and second one is the pooling layer. So multi-channel aggregation layer is the exact substitute for the convolution layer, which is used for performing supervised learning on graph structure data. So you have a graph structure data, so you can find the relationship between input and output using the mag layer. So as you can see that we are extending the concept of channels in CNNs to arbitrary inputs. And the second operation you can see is the pulling and unpulling. They are the same. They are basically allowing you to learn efficiently through the reduced representation of the input arbitrary graphs. So let's get into the details of each. The first one is the multi-channel aggregation layer. So as I described earlier, multi-channel aggregation layer extends the concept of localized operation in CNNs. But there is one major difference that MAG has when compared to the CNN is that MAG uses a different set of weights at different locations. So if you look at the transformations of the layers, for the MAG, if you see these are basically the learnable parameters, kernel parameters, and it has this I index which stands for the spatial location, which is what I have removed here. CNN, they don't do that. You saw in the earlier animation that the same window was sliding across the domain. So you are using the fixed set of window and the same window slides throughout the domain, which is not the case in Mac. So which has its own pros and cons. For example, for the people in mechanics, imagine that you have a, let's say, a bimaterial problem, a beam that you're deforming, and you know that the kind of deformation, the pattern will be different depending on the region of material. But because in the CNNs, the same window slides across, it performs a very similar transformation irrespective of the materials that you have. So you can give the external information about the non-linearity of the spatial region, but here we thought that we might not need that because we are already have a different set of weights which will take care of the spatial non-linearities. So MAG, why we named the layer as MAG? Because the convolution name usually has the notion of sharing the parameters, and therefore we chose not to use that, and we call it as aggregation layer. We are performing some weighted aggregation that you saw in the earlier slide, but it resembles quite closely to existing spatial graph convolution layers. Now, there are multiple of them, and I'm just pointing out some of the very important or famous ones. For example, the graph convolution layer by Kiff and Welling. This is quite popular. What it does is it performs first the averaging in the neighborhood of a node, and then it multiplies with some sort of shareable weight. So you can see that it's already losing some information because you are not performing a learnable aggregation, what we did in Mac. And there is a very popular extension called Graph Attention Network, which has been directly inspired from the attention module in the transformer neural network. So if we try to decipher these in terms of our notation, and so for a given input, you have one shareable set of weights, but also you compute the relative importances of these weights with by taking the feature value also into consideration. So GAT layer differs from the other layers in the sense that it also considers the feature information in performing the aggregations. So MAG most closely resemble to semantic GCN layer. So when we came up with MAG, we thought that this is really cool that this thing doesn't exist. I mean, the concept of the multiple channels in the graph convolution layer, and we thought we did something really nice and will be appreciated a lot. And somehow I failed to see that it already existed a few years ago, which I found out while doing the extensive literature survey while writing the paper, and it has been used for the particular computer vision applications of post-registration. So MAG is very similar to semantic GCN because they also have this concept of higher channels, and there's this extra step that they also multiply with some sort of a learnable weight matrix, and this alpha beta stands for the channel dimensions of input and output. You can have the thorough look at these things in the paper. I'll share the link soon. So to conclude, the MAG has the most efficient and a very effective message passing scheme. And also it can be used interchangeably with all the existing neural network here, including graph convolution, dense, or convolution, whichever you name. So now look at these simple mesh. You want to, let's say, pass on the information, nodal information, feature information from point B to C. This can be relevant because let's say you are applying the force on this node and you want to know how it affects the node C. Now, because MAG exhibits this concept of localized operation, you need to have multiple of them in order to convey the information from one topological end to another one. And you can already guess that this is what makes it a bit computationally expensive. One way to reduce the number of application is to use the higher window size. But by doing so, basically you are converging more and more towards the fully connected network, and which is not desirable. So overall, this is computationally expensive procedure, which is what inspires us to propose the pooling layers. So the pooling layers that we have proposed are the type of clustering type of pooling, where we try for a given input graph, we find set of non-overlapping subgraphs or cliques, and then we pull over them. So for example, for this particular mesh, we found these colored subgraphs, and then you just either perform maximum or minimum on average on all the nodes present in this region. And the unpulling operation is exactly reverse of that. You replicate the values from the pulled node to all the nodes that are present in the particular subgraph. So how we do that? It's not that complicated algorithm that we came up with. So first you choose a point, and now you randomly choose a node which is connected to this point, so which will be this. Now you again randomly choose a node which is connected to both of them, which will be this or this. We choose this. It's a random selection. And now we have a complete subgraph. Now there is no node which is connected to all. So we just completely take it out, including these connections. And now you keep on doing that until you reach zero nodes. And that's how we generate the list of subgraphs. They are one more point is that we are doing it a priori while defining the network. So we define these subgraphs, and based on that, we define the pooling layers. So once, so for a given mesh, we finalize the pooling layers before even starting training of the network. So this is the algorithm you can go and see here. I won't get into the details of it. I just explain the idea behind it. So now let's go back to the same problem of these information passing from node B to C. And you can see that now in the pull space, I can just apply two MAG operation, two localized operation. And if you visualize in the higher space, they are sufficient to transform the information from one into other. So which is what makes it computationally cheap. One more point, that both MAG and pooling and pooling layers, they are now they are written in TensorFlow, and they support also the batch training. Now let's go to Perceiver IO, which is one of the state-of-art transformer-based models. So this work has been done with my fellow PhD student Ian. So Perceiver IO is originally it was designed or proposed to handle multiple type of inputs and outputs. So imagine that you have input of images, videos, audio files, and the Perceiver, without need of extra modifications, it is quite robust to handle these kind of what they call multi-model inputs, and also predicts the multi-model outputs. So Perceiver IO is better compared to transformer models in the sense that it uses this latent space representation, which would be the same irrespective of the input size. So it scales linearly with the input size, as opposed to transformer, which scales with the square of the input size. So now, if you compare Perceiver IO with Magnet, or the kind of existing graph convolution layer, how it differs is that in Magnet, you are giving externally the information about the topology of your input, and you are kind of performing very smart forward passes And in case of Perceiver IO, it tries to find the relative importance between the inputs through these attention modules. So, so it has its own pros and cons again, because if you have, like, we observed that if you have really, really high inputs, in those cases, Magnet and CNN based approaches, they perform better because you are externally providing how you have to perform these local operations. And then at such times, Perceiver struggles a bit. But again, to compare it to Magnet, it also has this encoder decoder type of architecture. So given a high dimensional input, you you use the latent representation, you find the latent representation through this attention module, and then you have these processing blocks. Usually you use multiple of them, and then through the decoder, you get back to the original shape. So a bit about datasets. In this presentation, I showed the implementation to these three kind of datasets where you have traction forces as well as body forces applied on quad as well as very arbitrary tetrahedron. And this is the breast deformation problem that some other members in the team quite extensively work on. So these are the degrees of freedom and the sizes of the data as well as the properties of material. One point I should mention is that all the implementations in this work are done in a data-driven way, that we are not really incorporating any type of physics information, because we are working on the architecture level, and the physics informed part usually comes through the loss level, so it can be easily extended. The magnet can be easily extended to a physics-based version. So just now I mentioned we are using a naive training loss, where we are just trying to fit the displacement. So for a given input force F, we predict the deformation using the choice of neural network that we have, and then you minimize the squared error. And while testing, we just take the absolute error for each example. So you take the absolute difference between the prediction and the true labels, and you take the mean of that, and that will be the mean error of that example. And then you also, to represent the performance of the entire test set, you also take mean error of all the mean errors. So these are some of the results. No worries. Don't get scared by just looking at the numbers. So we have three type of networks that we use for 2D domain. We mentioned that CNNs can be used for only structured inputs, which is what we have done here, and the magnet and Perceiver, they work for both. And we can see that Perceiver IO and CNN are doing quite nice compared to the magnet in this particular example. Just one point, I have also described the maximum nodal displacement. So which means for each example, you compute the nodal displacement of every single node, and the maximum nodal displacement of that example is the maximum nodal displacement. And then for the entire test set also, you get one number, so that is what it represents, the maximum nodal displacement of the entire test set. And you can see that the mean error as well as these are the outlier maximum errors for a particular degree of freedom prediction, and you can see that already the errors are quite low. And this is another toy example, the elephant example, for which also the maximum nodal is 140 meters, and you can see that we have quite low mean as well as the maximum errors of the prediction. And for the breast example, we have similar result. For this, I only implemented magnet, which was a part of another paper. So, but the moral is that all the networks are able to do a good prediction on the entire test set. What we are doing is also we are sorting all the mean error for every single network with the ascending order of maximum nodal displacements, and then we will visualize only the example with the highest nodal displacement, which most of the times has high error. We found the correlation between the errors and the maximum nodal displacement, and you can see that these are also not so much sensitive to the displacements. So just simple visualizations. So you have the 2D problem, you are applying some traction forces and on that region, and the green node has the maximum nodal displacement of 0.35 meter. And you can see that the error of predictions are quite low when compared to this maximum value. So these are basically the error counters, which stand for the absolute error between the neural network and the FEM solution, as we described in the equation earlier. So another similar application for the breast problem. This is a bit complicated also because you have like very high nonlinear deformation near these fixed boundary condition, and still we are able to predict the deformations, and this is all actually the worst prediction example. It's which is also quite acceptable. One point to mention again is that during the training, as I mentioned, we did not use any physics relevant information about the boundary conditions, and we can see that implicitly the network is able to learn the boundary condition, and it's doing quite good job in tracking this fixed boundary condition. Also, we plotted the reaction forces that are generated at the fixed interface using these data-driven approach, and we can see that magnet is doing quite decent when compared to the FEM solution. And of course, the performance can be far improved by incorporating this relevant information about the residuals as well as these fixed boundary condition in the training procedure. But that's out of scope of the present work, which will be done soon. Similar visualization for the 3D elephant problem. Again, we are applying a body force, and the green node has the displacement of 140 meters, and you can see that the errors are quite low compared to this number, which fall much below 1%. So all the now training and inference time. This can be interest of many of us. So if you look at the training times, you can point out that the Perceiver IO specifically takes quite some time to train, but once trained, it's extremely fast in doing inferences. So the size of the inputs in our cases is comparatively so less for these kind of architecture, is that it's almost taking similar time for these both 2D and the 3D problem, and you can also subsequently see the finite element prediction times. By the way, these are the prediction time for the single prediction, not the batch mode. So to conclude that, yes, Perceiver IO, though it takes more time to train, but it's quite fast at the inference. But also, if you look at how the training goes on, what we observed is that for the magnet and CNN, you a priori know how the topology of the mesh is, and therefore it learns a bit faster. I mean, the loss goes down fast, and then further it slightly decreases towards the end. But Perceiver IO, on the other hand, takes time to reach to the optimal solution, but then it's extremely fast when it does so. Another issue we observed with Perceiver was if you go beyond a certain input size, and then Perceiver failed to learn at all, which was around 10,000 degrees of freedom, and in that case, Magnet and CNN comfortably learn the solution because we already know to perform these forward aggregations in a smarter way. So all the codes and the data sets presented in this work are available on GitHub as well as Zenodo on these links, and you can get a detailed look of the implementation as well as the idea behind Magnet in these papers. So you can also find all publications on my website at one place where you can just go through all of that at one place. So basically, it will be convenient. So thanks a lot. I am open for questions.
Thank you, Saurabh. So I'm opening the questions part.
Yeah.
Whoever wants to ask questions, I can see Vasilis is raising the hand. So please go ahead, Vasilis.
Hello, thank you very much, Saurabh. It was a really interesting presentation. I really like the comparison between the different methods. I do have a few questions.
Yes.
First of all, about the Perceiver IO.
Yeah.
So what is the novelty there? You said, well, the difference between like the magnet, did you say that it's agnostic of the topology somehow?
No, so okay. For Perceiver IO, we are using the existing architecture. I mean, the name itself, the Perceiver IO. If you go to this reference, you'll find it, and it basically has attention modules as you have in any transformer architecture. And Magnet is very different. It's kind of graph neural network, and Perceiver IO is a kind of a transformer model. That's how they differ.
Okay, very good. And can you comment on the memory required for train the Perceiver IO?
Memory is comparatively low. If you look at the number of parameters here, let's go here. You can see that the number of parameters that we have used for the Perceiver is comparatively less when compared to Magnet and CNN. In particularly, Magnet is quite memory hungry, the way we have implemented the network. Yeah.
Okay, yeah, I'm familiar with this problem. I do face it every day.
Yeah.
Okay, and can you also give me a few more, can you at least go back to the slide where you explained the MAG convolution and explain it one more time for me?
Yeah. So what we are doing in convolution is we have these input channels and you're applying the filter throughout the channels as we usually do, and you are basically doing the weighted sum, right, with the learnable weights and the inputs. That's what we are doing.
Yeah.
And you go to next hop and you slide it, you do the same. And in Magnet, you're doing something similar. So you, based on the adjacency matrix, we are assigning weights only to these non-connected nodes, and we are then performing the sum in the local region, the weighted learnable sum. And we do that on every channel dimension with different set of weights.
Okay, I see. Thank you very much in that case. Good luck with the publications. And yeah, wish you luck in general. Thank you.
Yeah, thanks, Ed. Thanks, Vasilis.
I can see a question from Chintan. Chintan, do you want to say it, or I should read it for you?
I'm just trying to see how can I access the.
Okay, so I will read it. Hi, Saurabh. Thanks for the very interesting presentation. I want to ask that have you performed a time analysis with respect to refinement of mesh? How your training time and inference time increase compared to FEM?
Okay, so basically I try to answer it in this way, that what would be the rough time complexity of this mag layer, let's say. That would be one way to put it. And it depends on how many edges that you have, because we are assigning the weights based on the edges you have. So it grows linearly with the number of edges. And so yeah, that would be the answer. But again, the way we have implemented Magnet at present, it's suboptimal. And if I compared this to, let's say, the existing, let's say, the convolution layer, which are super optimized, I observed that usually Mag takes 2 to 3 times or 4 times training time when compared to convolution. Now, going back to finite element question, I haven't really performed an extensive analysis that how the time it took for the how it scaled with for the finite element simulations. But yeah, in case of the magnet, it grows with the number of edges, and the storage requirement, they grow with the size of the adjacency matrix, which is with the number of nodes.
Perhaps, Saurabh, maybe if you could show this table with the timings in the end of the presentation.
Yeah,
maybe here you can see the relative
yeah.
time, the FEM versus neural network prediction time. And for the 2D domain, this ratio is higher, FEM time versus neural network time is higher than for the sorry, lower in that lower than for the 3D problem. So we can see the tendency that the gain is increasing when you have a bigger problem.
Yeah, but it's also intuitive, as I explained earlier, that because we are using the incremental loads, the higher the inputs you have, finite element solvers, they take more time to converge. And in case of these neural network approaches, which are pre-trained, it's the same prediction time irrespective of the input forces that you have. That's also one point to notice.
Maybe also about the scaling with the increasing problem size. Perhaps there is also another point to mention, that perhaps if you have a much bigger mesh, so refined discretization, perhaps you need to add some more layers to coarse grain the model. So this can bring a bit more the complexity, or time complexity is a bit above linear. It is not scaling with the number of nodes, but maybe some n log n or something like that.
Maybe, yeah. Yeah, at the end, it's about the number of parameters, and I said that's why I said that it depends on the number of connections, edges you have. So,
and there's a question from Michal. Do you want to read it, Michal?
just I'll stop. Please, can I? Oh, sorry.
Okay, let me read the question of Michal. How would these approaches compare to approach storing and reusing the LU factorization and quasi-Newton methods? What is the intended use case here?
Okay, so as I mentioned earlier, we are interested in finding surrogate model for particular applications. And it's a direct mapping between the forces and the displacement that you predict. Of course, the conventional Newton-Raphson methods, they are very general and universal, and they work for any type of input. That's what one of the limitations of this method is. In this case, you are just trying to find some sort of surrogate model knowing the pre-computed solutions. So that would be the answer to Mihail's question. And Jack asked that, have I compared to other approaches? No, I haven't. At this stage, I haven't really compared the performance of Magnet or even Perceiver.io to other problems apart from solid mechanics. But maybe, Mihail, if you have, can you just unmute and ask your question, so it's also easy to have the conversation and answer it in a better way?
Yeah, can you hear me?
Yeah.
I'm just very practically motivated, right? So
yeah,
working on the industrial problem. So what I had in mind is you say for nonlinear problems, right? You directly want to find a solution to a nonlinear problem, avoiding any iterations, right?
Yeah.
But the standard approach would be to probably approximate the nonlinear operator at some iteration, store the factorization, and reuse it for a fixed number of iterations, maybe then compute it again, right? Like the classical.
Yeah, maybe. Actually, we have another idea we will be soon implementing. That is, we will actually combine this architecture that we discussed with directly residual computations, and we will perform these standard methods, and we will just give input force and minimize these residuals and optimize the parameters of the network accordingly. That would be a better approach than these naive displacement-based fittings.
Have you looked, for example, at the memory complexity of how much memory do you need to store the parameters for these networks, comparing to how much memory would be needed to store the factorization, something like that?
No, I haven't checked that, but I'll do it. I'll let you know.
Okay. Yeah.
But it's huge. It's not super optimal in case of magnet, at least.
Okay. Yeah, thanks.
Yeah.
Yeah, Michael, so just to maybe touch upon your comment, those sort of architecture like CNN UNet and Magnet UNet, to some extent resemble this multi-grid scheme. So you can have an interpretation of them as being a sort of tunable solution scheme or preconditioning scheme. So you can look at them as those. Normally in the multi-grid, you have some predefined fixed weights or iteration metrics that you use, and then force graining and sampling operators. And here they are to some extent trainable. So perhaps they might be better to directly solve some more nonlinear problem, because multi-grid works well for approximating or preconditioning the solution of the linear problem, linear system of equations. And here you have a fully nonlinear problem that tries to be approximated. So that's my, let's say, intuitive understanding how this can be understood.
Mm-hmm. But there are also these approaches where people have used, let's say for this multi-grid problems, they use these optimized neural network weights as the first case of your Newton-Raphson iterations. There are these approaches also. And it's quicker to converge in that case. I can actually put the links of the repository here if someone is interested.
Yeah, maybe we can also put your presentation on the website.
Yeah, sure. I will share that. So these are the two repositories which have implementation of all the example that we just talked about.
Anyways, I can see no more questions today.
Mm-hmm.
So thank you so much, Saurabh, for presenting the results, and thank you all for attention and for the discussion.
Mm-hmm.
I will keep you posted about future machine learning seminars. And for today, have a good day and see you next week.
See you guys. Thanks. Bye.
Thank you. Bye.
Bye.